Imagine a vast, dark, and cold expanse in space. This wasn't just empty space, though. It was a giant cloud, a nebula. This cloud was truly immense, stretching for light years across the cosmos. It was made mostly of hydrogen and helium gas. These are the simplest and most abundant elements in the entire universe. But there was also a sprinkle of dust. Tiny grains, smaller than smoke particles, made of heavier elements. These elements were forged in the hearts of ancient stars, long dead. Those stars exploded, scattering their guts across space. This cosmic dust became the raw material for future generations of stars and planets, including our own Earth. The nebula wasn't perfectly uniform. Some regions were slightly denser than others. These tiny variations in density might seem insignificant, but in the vastness of space and over immense timescales, they matter a lot. These slightly denser clumps had a little more mass. And where there's mass, there's gravity. Gravity is the universal force of attraction. It pulls everything with mass towards everything else with mass. It's the invisible hand that sculpts the universe. This gentle pull, almost imperceptible at first, began to tug at the particles in the denser regions of the cloud. It was the very first step in a long cosmic dance. So picture this cosmic stage, a colossal cloud of gas and dust, cold and dark. It's enriched with elements from long-gone stars. This is the stuff of future suns and worlds. Our story, your story, starts with this magnificent primordial cloud. Gravity, the silent architect of the cosmos, began its work. In those slightly denser regions of the nebula, the gravitational pull was a tiny bit stronger. This extra pull started to draw in more gas and dust. As more material gathered, the mass of the clump increased. And as the mass increased, its gravitational pull became even stronger. This is a classic feedback loop, a runaway process. More mass means more gravity, which means pulling in even more mass. It's like a snowball rolling downhill, growing larger and faster. This process, known as gravitational collapse, was slow at first, taking millions of years. As the cloud began to collapse, something else started to happen. It began to spin. Why? Because of the conservation of angular momentum. Think of an ice skater. When a skater pulls their arms in, they spin faster. The initial nebula wasn't perfectly still. It had some slight random motions. As gravity pulled the material inwards, the cloud shrank. And just like the ice skater pulling in their arms, the shrinking cloud began to rotate faster and faster. This spin was crucial. It prevented all the material from simply crashing into the center at once. Instead, it began to flatten the collapsing cloud. The spinning motion caused the cloud to spread out into a disk shape. The Great Collapse had transformed a diffuse cloud into a structured, spinning system. At the very heart of this spinning protoplanetary disk, the real drama was unfolding. The central region, the protostar, continued to accumulate gas and dust. It grew denser and hotter. The pressure at its core began to build to unimaginable levels. Think of all that material pressing down from all sides. For millions of years, this protostar was just a very hot, very dense ball of gas. It was glowing but not yet a true star. It was shining because of the heat generated by its ongoing contraction, like a cosmic ember. But it wasn't producing its own energy through nuclear fusion yet. The temperature and pressure in the core of the protostar kept rising. Eventually, after about 10 million years or so, a critical point was reached. The core became so hot, around 15 million degrees Celsius, and so dense that nuclear fusion ignited. This is the moment a star is truly born. Hydrogen atoms, the most abundant element, began to fuse together to form helium atoms. This process releases an enormous amount of energy. This outward rush of energy from fusion finally balanced the inward crush of gravity. The collapse stopped. Our sun, a stable, shining star, had lit up. While the sun was igniting at the center, the rest of the protoplanetary disk was a busy construction site. The disk was still full of gas and dust, the leftover material from the sun's formation. These tiny dust grains, initially microscopic, began to stick together. It's a process called accretion. Think of dust bunnies forming under your bed, but on a much grander scale and driven by gentle collisions and electrostatic forces. These tiny particles clumped to form slightly larger particles, then pebble-sized objects, then boulder-sized objects, and so on. It was a slow, patient process of growth. These larger objects, ranging from a few meters to kilometers in size, are called planetesimals. They were the building blocks of planets. There were millions, perhaps billions of these planetesimals orbiting the young sun. They frequently collided with each other. Sometimes these collisions were destructive, shattering the planetesimals back into smaller pieces. But other times, especially if the collisions were relatively gentle, the planetesimals merged and grew larger. Gravity played a key role here too. Section 5. Evolving Ideas. From Laplace to Modern Science. The idea that the solar system formed from a cloud of gas and dust is not entirely new. As far back as the 18th century, thinkers like Immanuel Kant and Pierre-Simon Laplace proposed early versions of this nebular hypothesis. Laplace, a brilliant French mathematician and astronomer, suggested that the sun and planets formed from a rotating, contracting cloud of hot gas. He envisioned rings of material being shed from the spinning cloud, which then condensed to form the planets. This was a remarkable insight for its time, based on observations of the planet's orbits and the sun's rotation. However, these early theories had their limitations. They couldn't explain certain features of the solar system, such as the distribution of angular momentum. Section 6. Seeing is Believing, Telescopes and Cosmic Nurseries. One of the most compelling lines of evidence for the modern nebular theory comes from direct observation. Thanks to incredibly powerful telescopes, both on the ground and in space, astronomers can now peer into distant stellar nurseries. These are vast clouds of gas and dust where new stars are being born, just like our sun was billions of years ago. Telescopes like the Hubble Space Telescope and the Atacama Large Millimeter-Submillimeter Array, or ALMA, have captured stunning images of protoplanetary disks around young stars. These disks look exactly like the theory predicts flattened, spinning structures of gas and dust. These images are not just pretty pictures. They are data-rich gold mines. Astronomers can study the size, mass, temperature, and composition of these disks. They can even see gaps and rings within the disks. These features are thought to be cleared out by newly forming planets, sweeping up material as they orbit their young star. It's like watching planetary construction in real time, albeit millions of light years away and millions of years in the making. Section 7. Worlds Beyond, the Exoplanet Revolution. The discovery of planets orbiting other stars, known as exoplanets, has provided another powerful line of support for the modern nebular theory. Before the 1990s, we only knew of the planets in our own solar system. We wondered if our planetary system was unique or common. The nebular theory predicted that planet formation should be a natural byproduct of star formation. If stars form from collapsing nebulas that create disks, then many stars should have planets. The exoplanet revolution has shown this to be spectacularly true. We now know of thousands of exoplanets. These exoplanetary systems come in a stunning variety. We found hot Jupiters, gas giants orbiting incredibly close to their stars. We found super-Earths, rocky planets larger than Earth but smaller than Neptune. Section 8. Our Stardust Selves, a Universal Connection. When we talk about the modern nebular theory, we're not just discussing distant astronomical events. We're talking about our own origins. Every atom in your body, except for the hydrogen and some helium, was forged in the heart of a star. Think about that. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was created inside stars that lived and died long before our sun was born. These stars exploded as supernovae, scattering these newly minted heavy elements across the galaxy. These elements then became part of new nebulas, like the one that formed our solar system. So, the dust grains in that primordial cloud, the ones that eventually clumped together to form the Earth, were made of this stardust. You are literally made of stardust. Section 9. The Ongoing Creation, a Universe Still Forming. The story of star and planet formation, as described by the modern nebular theory, is not a tale confined to the distant past. It's a story that is still unfolding all around us, throughout our Milky Way galaxy and in countless other galaxies across the universe. The universe is not a static, finished place. It is a dynamic, evolving entity, constantly creating new stars and new planetary systems. The same fundamental forces, primarily gravity, that sculpted our solar system are tirelessly at work, collapsing new clouds of gas and dust. Astronomers, using ever more powerful tools, are witnessing this ongoing creation. We see young, brilliant blue stars illuminating the remnants of their natal clouds. We observe protoplanetary disks, the telltale signs of planet formation, around many of these infant suns. Each new observation reinforces the central tenets of the nebular theory and adds new details to our understanding.